Hi. I hope everyone had a nice, whatever it was, fall break, a few days, or at least one extra day, and you're well rested and whatever else. Any questions before we get going? Is the lab due before class on Friday? Send it. It's just it's due on Friday, and we'll talk about that briefly. I mean, I guess we're talking about it now, so we don't need to do any briefing later. But yeah, send it to Nathaniel. Email it to Nathaniel on Friday at some point before the day is over, unless he gives you different instruction. Right? So if Nathaniel gives you whatever instruction Nathaniel gives you as the GA leading all of the labs, that trumps mine. My hunch is just submit it anytime that day. But if he gives you some different instruction, then follow that one. But if you haven't heard from him about particular due dates or anything, just before the clock strikes Saturday, so before midnight, I assume at 11:58 p.m. he'll be getting some labs. But work on it, work on it throughout the week, and just don't because it can take time. It can take time to get SPSS up and working. It can take time to get it installed, and sometimes people will have some compatibility issues or whatever glitches they need to work through, and you don't want to try that on Thursday and then realize your computer is incompatible and then be calling up friends and calling up the help desk. And so just be proactive and kind of pre-proactive, right? So get it done as quickly as you can. And we'll talk about the analyses today a little bit, though. So we're here, right, on October 5th, and we'll start talking about these analyses we're going to be running this Friday. The lab is due, and then we're going to move on to regression modeling soon. But today we're just going to talk about the lab statistics and sort of how I'm not going to run the lab statistics specifically, but I'm going to show you how it's done. And then the research topic is due on the 14th. So remember, that isn't that far away. Lab 2 is due that Friday. So just be making progress along the way. October 21st, we have our second exam, the second mini boss. Will there be a link to on Canvas during lab? Nope. Send it to Nathaniel. Just email it to Nathaniel. And he'll be doing the grading for those. And this is our breakdown of points, as you know, the readings, in case you feel like doing the readings. There's just a few for this section, and it gets slimmer and slimmer as we go. Is the research topic individual in groups? Submit that in groups. So research titles, right? Again, October 14th, you can submit those in groups, but make sure every single person's name is on it. Don't leave anybody off. Otherwise, I don't know who to assign points to, right? So make sure you're really clear with who's in your group and your question at that point. And so a few people have let me know that they have projects and sort of questions and are coming together. I don't have any exact groups. I know Ricky's going solo, and I know there's a couple of groups. I don't know all the group members yet. So we have an and others and same and and. And so at your convenience, it's not at your urgency yet, at your convenience, if you come up with your groups, just let me know those groups and let me know those questions, and I will get everything posted. And we can talk about them in class as we talk about refining research questions. I'll talk about your questions. That will be the example that I use as I'm discussing the merits and improvements of a particular example question. So there's going to be at least 12 posters. So I'm not going to be able to contribute at the level of the poster. So right now, make sure that you are learning the statistics. You are learning data management and sampling and reporting. And just as we move forward, we've done the history of statistics. I'll reference historical bits as we move forward, but we've talked a lot about where statistics came from and political arithmetic and all this stuff and the John Snow stuff. We talked a lot about how we got to today. And now we're going to be talking about what to do with today's information from an epidemiological perspective. And then in the final section of the class, we're going to get into how to write grammar and kind of literary tricks, and sort of the recipe of more effective writing. We'll do a couple of lectures on that part, as well as ANOVA and randomized controlled trials and what comes after epidemiology. But right now, we're going to start doing these kind of proper epidemiological surveillance statistics, not just cohort studies, not just stuff like that. Uh, but regressions and t-tests and the mathematical models that SPSS will do for you. So there's a couple of example posters that are uploaded. This is essentially what you're going to be making. You have a group doing it. We did this one a couple of years ago, so if you want to use this as a good example of how to do it, this is a very effective poster. I referenced this in the last lecture. I think I've referenced it a couple of times. It's using Sparta data. And but what we did here, this one was presented in Florida 2 years ago, year and a half ago, over the summer in Orlando, and published. The abstract was published in Medicine and Science and Sports and Exercise, good journal. But you're going to go section by section. So you begin with the background, and in the background you'll have citations, right? You see there's like a little 8, and there's a 5 through 7, and there's the 1 up here, and the 2 and 3 and 4. And so you'll see these little citations. I don't care how you cite what I'm APA. I really don't care the tiniest bit, your citation format, because no matter what journal you submit to, you have to change the citation format to fit that journal. Just be consistent. Pick one and be consistent. Who cares which one you pick? Invent one. I don't care. But be consistent with how you're making your citations. Now, most of your citations may be coming from a single meta-analysis. That's okay, right? That's totally fine. But you might have a couple of additional claims about the history of your phenomenon or something. And if it's on, say, COVID, I don't think there are meta-analyses out there yet. It's so new. I don't know that any meta-analysis that we've had time to amass all of the data. I mean, those things take forever. So you're probably going to have multiple citations, but write your background. It's well cited. You're setting up the problem. At the end of that, you write a purpose. So the purpose, right, for this one was to evaluate the effectiveness of Sparta kinematic sequencing in predicting in-game performance of collegiate basketball players. So you have your purpose, and it's just a single sentence followed by your methods, right? You have your background, and then you have your purpose, your introduction or your background, and then your purpose, and then you get into methods. And don't talk about the exact statistics here, just talk about the sort of utensils, talk about the instruments, and talk about sampling and how many subjects you have and the nature of the experiment in a methodological perspective. That goes in the methods section. And so for the Sparta stuff, it was like, all right, what is load, explode, and drive? And we're comparing to vertical jump, and what are these things, and how many players are there, and how many observations, right? Observations are different from players. There are 62 centers. For the How many total players were there? 37 players. So 37 unique players. And those players had a ton of observations. They were tested and retested and retested and retested. Now, the statistical analysis section, this is where you talk about using SPSS and the regression models that you used and what were your dependent variables, stuff like that. You don't provide any results. You just say, here's what we did, right? Significance was set at P is less than 0.05. Put that in there, because that's part of that rigidity of statistical phrasing, right? In the parlance of a statistician, P is 0.05. That's sort of this Moses coming down the mountain with law. We've just accepted that 0.05 is doctrine. And obviously, that it's not in any practical or meaningful way. And even Fisher, who said 0.05, gave it a wide berth, right? Gave it a lot of room. But Always just say that in your statistical analysis section. And then you get into the results, right? You do everything and then do your results. So the beta, the unstandardized beta, we've talked a little about this. In a regression, this is the effect size and this is the significance. So this is just a basic results, all descriptive, no images or anything in the results section, and looking at these different outcomes. And then you have your conclusions. Once the results are over, you get to your conclusions and wrap everything up. This is the wrapping paper, the bow. You're really stating, you look back over the poster, over everything that just came before the conclusions, and you sort of introduce and conclude and just have this nice conclusion. Just watch a movie, and in the first act, everything is concluded by the last act. Read a book, read like a mystery novel or something, and there are all these mysteries introduced in chapters 1 through 10 or something, and these questions asked, promises made, and all those promises are resolved, questions answered, mysteries revealed by the last chapter, in those concluding chapters, and maybe an epilogue or something. And so that's what you do with the conclusion. This is your final chapters and epilogue, and you wrap up everything, and but sort of descriptively. um, Now, in the center column, there were a ton of tables. Now, tables 1 and 2, this is descriptive stuff. You're going to do this for your lab. For lab 1, for every lab, actually, you will do this. You will do descriptive tables where you characterize the samples. You characterize who you tested, right? So freshman, sophomore, junior, senior, right? What we had for each class: 16, 16, 18, 13. Those were the years of players. The positions, right? Guard, center, and forward. Those positions, fewer centers than guards and forwards, but pretty evenly distributed across classes. And the season looked at 4 different seasons, evenly distributed: 15, 15, 15, 18. And using this load, explode, drive, Sparta kinematics to see if it predicts in-game performance. Now we have our regressions. Now these tables, this is 4, 5, and 6. These tables do not look like a SPSS output. Never copy and paste in an SPSS output into your poster. I'm going to say that again, just so that I hope nobody does it. Every year people do this. So once again, make a mental note of this. You don't have to write it down. You'll remember this. Never, ever, ever copy in to a poster, to a final draft, to a submission, whether it's a manuscript or a poster or whatever. Never copy and paste in an actual SPSS output. They're just sloppy. They contain a bunch of data nobody cares about. And it just looks like the person putting them in there has no respect for the reader, because I can't even go through the effort to make this palatable, right? So it's like, I'm going to cook you dinner. Here's a bag of flour, and here's some butter, and here I didn't bother to cook it, but here's just a pile of flour. Eat that, right? So it's almost rude to your diner. So that's why this doesn't look anything like an SPSS output, because it looks good, right? This is what you're supposed to do. You don't have to make it look like this, but make it look like something. Make it look like something presentable, something with nice aesthetics. So let's start here. Regression. This is a multiple linear regression with vertical jump, load, explode, and drive as the predictors. There are 4 predictors predicting the dependent variable, which is assists per 40 minutes, and nothing significant. Load, explode, and drive, they don't predict assists. And with R squared, meaning you're predicting 12.7%, but insignificantly. I mean, it's not even the overall model isn't significant. So this whole thing, load, explode, drive, whatever, this doesn't do anything. This one, regression, multiple linear regression, estimating the effect of Sparta and vertical jump on blocks per 40 minutes. So load, it looks like there's a tiny increase with a p is 0.021, so it's significant, but you're getting an additional 0.03 blocks per game. So how many games would you have to play to get an additional block, right? And nothing else is significant there. And here we see regression estimating vertical jump on rebounds per 40 minutes. So again, load, you're getting an additional 0.182 rebounds per 40 minutes. So it's not much of an effect that you're seeing, and a lot of the effects you see, like if we go back, it's non-significant. But explode, that beta is actually higher. The better your explode, the fewer rebounds you're getting, and that one's close. It's not quite significant, right? But it's trending. It's essentially there's a wider standard deviation is usually the explanation. If you have the same number of subjects, there's more variance, there's more scatter, and so you get a little bit less significance. But as explode increases, athletes get about half with each additional point of explode. You get about half of a rebound per game less with drive with each addition. So if you get 2 additional points of explode, you go down a full rebound per game. You can say the same thing about load going up, 0.18. Drive is going down a quarter of a rebound per game with every additional point of drive. Now, vertical jump goes up an additional whole rebound per game for every additional inch you get, but there's some deviation, and an inch is a lot more than 1 unit of load there. And so you look at like explode throughout, assists is going down, increase explode and your assists go down. Blocks per 40 minutes, increase your explode and it goes down. Rebounds per game, increase your explode and it goes down. But a bunch of non-significant stuff, and where you see significant increases, it's just so marginal. So it's sort of, we just assume it doesn't do anything. But the data were actually pretty good. When you look at, there's an outlier here and there, but for the most part, there's these nice distributions. The QQ plots, if they track those QQ plots really beautifully. And so what happens whenever you're working with the private sector, whenever you're working with industry, if someone's going to lose money on your finding, they attack you. Now, what is graceful about the Proteus people, Sam Miller is the CEO of Proteus, and I've done a lot of publications with Proteus, and I don't care whether I find something good, whether I find something bad. I give you an exact quotation of Sam Miller, the CEO. Word for word, he said this to me in an email, and I copied and pasted it into this slide. Good or bad, I don't want to be involved. That was the CEO of Proteus. Now, the CEO of Sparta, I decided not to put his whole email in. I went and found it, and it was too damning. In part, it's protecting myself. I don't want to deal with the scorn of I don't want to have the wrath, strike me. But also in part, I would feel bad for the guy. Phil Wagner, he made a lot of comments that were revealed a lack of understanding of science and statistics and basic math. And if I put those quotations in here, I'm like an asshole. And so I didn't want to do that, but I just put in this. So this is his immediate responses. We have some, as soon as that basketball one came out, he noticed it, and like 2 days later, I got an email. 2 days later, a week later, I don't know how long afterward it was. It wasn't that long. We have some concerns about the accuracy of some of the results in some recent abstracts. There's a lot of some in that sentence, and then he went on to say some really wildly inaccurate things, and criticizing me, my students, the lab, the university. So he went on to say, first off, refer to himself in the third person as the doctor over, and then make a bunch of threats and false claims. And so he's probably a lovely guy, right? If you're not publishing something against Sparta, he's probably a totally lovely guy. But the problem is we run an ethical lab at Pacific, and no one's going to pay me to change that. Now, when you look at how Sparta does their science here on campus, on other campuses, there's Brigham Young and Kansas have some Sparta publications. They're paid for their results here on campus. The Sparta publications, other than mine, right, where I just publish whatever I find, there's a paycheck to compensate those findings. And so I don't think, sometimes I just assume everyone's ethical in life, and everybody is interested in truth. Everyone is interested in sound methodological practices. And I often forget that other people are making money, that there's a dollar to be made. And so if you remember Alex Avery over here making all these wild claims about the pesticide industry, that the pesticide industry doesn't cause frog mutations, and it doesn't cause upregulation of aromatase enzymes and the conversion of testosterone to estrogen. So making all these claims that it doesn't. Well, what did they do? They didn't put lids on the containers, and then they expose a particular group of frogs, and then everyone was exposed, and you have the mortality rate was outrageous throughout the entire. And so, but then knowing that they're making false claims, they're going to do it because they're going to make millions and millions of dollars, and let's quote Trump, billions and billions, right? So when there's money on the line, the industry reaction you get is not one that you want to not necessarily one you want to go up against. I just said, you know what? Fuck it. I'm not going to publish on Sparta anymore. This is just, I do this. I mean, you saw my QQ plots, right? I mean, the soundness of those methods were ridiculous. And to have opponents come and just attack you because they're losing money on your sound findings, I don't need that stress. And so I just put Sparta aside because it's very unlikely that I'm going to find positive things for it. Remember, I'm a muscle physiologist. I understand how this system works, and I understand what contributes to performance. And now I'm not a biomechanist, so I'm contained in my field, but my understanding of statistics and muscle physiology, I just can't imagine a universe in which Sparta is of the tiniest value. So not everything Sparta does is bad. No, I think you're probably right in that comment. Not everything Sparta does is bad. My encounter with them was a bad one. And I think it's probably useful for particular things. Now, is it more useful than a basic vertical jump? Most of it, though, in the comment box. Is it more useful than a vertical jump? And that's all I was talking about in that abstract. Maggie and my abstract. And the answer was no. You can just do a basic vertical jump, and how many inches do you get? And that's every bit as good of a predictor as Sparta is. And a vertical jump is, costs 0 pennies to do. And so that's all I was saying is maybe we don't need to spend all this money on advanced technology when good old fashioned vertical jump is just as sufficient. And so I agree with the next comment. Not worth money or even close. But again, it may be valuable for particular things, but I wasn't exploring those things. I was exploring prediction in basketball. And the response I got was about, we did studies. I'm a doctor, and we did studies with much higher statistical power. I looked them up, and 16 subjects, and it was a YouTube video. And I'm like, what are you talking about? And then something came out later with the YouTube video. I swear, and I haven't gone to it again because I don't want to give it views. I was the 380th view, and it was just a YouTube video. It wasn't a publication. And that was the higher statistical power claim that he made. And then something came out later between Brigham Young and Kansas, but it had 16 total players, and it was like silly statistics. It was really like I don't know, frogs without lids. I mean, it's silly selection procedures and stuff. And I'm like, I can't even argue with. And so in my response, I said, I'm not willing to engage in this, level of dialogue. And then I ended it. To his credit, he actually didn't respond to my response. But you're going to encounter this. If you do, well, you're not going to encounter it with Proteus. Again, let's quote the CEO of Proteus. It's like, not everything I find champions it. They don't care, right? Good or bad, I don't want to be involved. That was their CEO. And so there's a difference of ethics. And I would rather do research on ethical institutions and ethical minds that are moving those institutions forward. That said, I'm sure that Phil Wagner's a lovely guy, and he's probably like a good father and a good husband and whatever. I'm sure he's charitable in a number of ways. He works at a soup kitchen or something. I have no idea. I'm sure some of that stuff is true, and he's a lovely guy. And I published honest feedback and got this backlash of Alex Avery proportions of industry is always going to attack honesty if honesty takes a penny away from them. So just remember, there's all these resources are up in Canvas of how to do everything. G-Power, we'll talk about that later. I'll make sure that's up in your Canvas page, G-Power. Choosing your topic, remember, October 14th, get that topic in. Once you have the topic picked, you can do your background research. Steven Pinker here, remember his line about what are the chances that crop circles are made by aliens? That's not mathematical, so you can't run statistics on that, but p-values characterize everything else. These probabilities really characterize everything else. Now, as we get into SPSS and you start doing your own probabilities, you start doing your own statistics, you're going to have to become familiar with the format, the structure of SPSS, of these databases, and where to click, how to run analyses, what contexts call for this analysis versus that analysis, and what the outputs mean. So this would be a database. This database you have, and it's in the lab section on the lab one section. You can use this one for lab one if you'd like. Now this is in the variable view in SPSS. At the bottom, you'll have data view. You can click on that and it'll become blue. Or right now we're in variable view, and variable view is just a list of all your variables: first variable, second variable, third variable, fourth variable, age and sex or gender and race and whatever. And then the type of assessment, right? Whether it's scale, you have a bunch of continuous stuff over here. Ordinal, you know what that is. Nominal, you know what that is. And here in the values section, it's coded. So males are coded as 0. If you were to click on that in SPSS, not in PowerPoint, it would bring up and tell you females are coded as 1. So it looks like this. This is the data view, right? That last one was a variable view. So if you click on data view, it takes you here, right? Subject number. So each one of these is a variable. And here's your data, right? Here are all of your data. And so the race and relationship status and marital status. And in the variable view, stuff was coded. Relationship status, 0, probably no relationship. 1, in a relationship. It's probably that. It's probably binary. Race, I don't remember what that one was. And age, everyone knows what that means. Marital status, sex, again, 0, that's male. 1 is female. And if you're going to analyze, there's a menu bar up at the very top. And so SPSS statistics and file and edit and view and data and transform. Transform, the only reason you would use that, and you're not going to use it for this class, the only reason you would use it if you're creating a new variable. Let's create BMI. And what you have is height and you have weight as 2 different columns. Let's say you have height and weight, but you don't have BMI. You can go transform, and there's a little item called compute, and you can compute BMI, and it'll add a variable column. You're not going to do it for this class. I'm not going to make you. If you choose to, that's where you create new variables. It's actually easier to create new variables in Excel most of the time, depending on what you're doing. Data, if you're going to sort cases, right now it's sorted by subject number. But if you want to sort by age, you want to go, all right, I want the youngest people up top and the oldest people at the bottom. You go data, sort cases by age, and it would re-sort the database. But mostly what you'll do is analyze, use this analyze column. And regression, if you're going to do regression, correlate, if you're going to do bivariate correlations, compare means, if you're going to do that, independent samples or paired samples, t-tests, or just basic means, you can do that there. But descriptive statistics, this is how you start making your table 1, which Maggie had in her Sparta poster, and you will have in every lab and in your poster. Table 1 comes first, and so frequencies and descriptives, that's what you do here. We're also going to talk about explore, and we're going to talk about crosstabs. We'll do crosstabs today, and we'll do explore later. But frequencies and descriptives, these 2 options you click on. Let's start with descriptives, that second one down. This is for means and standard deviations. And so if you're going to do means and standard deviations, you want a bunch of continuous data. This little ruler in SPSS means continuous. So miles of commute to campus. What is your GPA? How many units are you taking? These are all relatively continuous. Okay, an argument could be made of how many units you're taking, but mileage. So all of these, what you do is you just double click on years of age, or single click on it and then click this to drag it over, and they all appear over here. So either double click on one of these variables or single click, it gets highlighted blue, and then click on this little arrow, and then they appear over here. So all these things appear over here. And then you just hit OK. So you just bring all of these these continuous variables over there, hit OK, and you get a big descriptive statistics box. The number of people that have that little, data cell So there's 104 subjects who had years of age. There are 110 subjects for whom mileage to campus was reported. Only 49 subjects reported their GPA. So not everyone reported everything. This was also from a merging of two databases, and one of the databases actually didn't have GPA in it. So,
Can I ask you a quick question?
yeah.
For the lab,
Mhm.
we can choose what we put in our tables, right? Like in our well, let me look at it now. Like the variables that we picked in our uh in the independent samples test, does it matter
It doesn't
which
matter what
variable?
variables. So for table one, you just pick a few things. You don't need to do a ton of them. You don't need to do all of them. Just pick a few and demonstrate that you know how to do it,
Okay,
that
so
you
the
know how
purpose
to run
of the
descriptives, you know
is
how to run
to
frequencies.
okay, cool. Okay, thank you.
Yeah, so whatever variables you want, as long as in the means and standard deviations column, you use descriptives, right? So miles of commute to campus, one person was commuting 55 miles, another person, a lot of people actually weren't commuting at all. And so the mean commute was 4 miles, give or take 10. Big standard deviation because anywhere from 0 to 55 miles, so there's a broad range. GPA anywhere from 2.05 to 4, but what you report is GPA is 3.3 plus or minus 0.5. That little plus or minus, I think it's Alt Shift plus on a Mac, and on a PC, I don't know, Google plus or minus sign and copy and paste it in. Don't do the plus and then highlight it and click underline. That just looks silly. Actually get the plus or minus sign in there. And on a Mac, I'm pretty sure it's Alt Shift plus. You just push that and a little plus or minus sign goes in. Or again, you can just Google it and say plus or minus sign. And then the sign comes up and you can highlight it, copy it, and then paste it in, and then change it to whatever font you have. But this is just means and standard deviations. So how much per year are you borrowing in student loans on average? $9,800 plus or minus 13 and a half thousand. So one person's borrowing $60,000 a year. Other people are borrowing no money a year. So looking at finances of all this. So mean and median, really basic. Let's go back to middle school here, elementary school. Just for the basics, I always love just making sure we hit the basics. Because people can tune out for a second and be like, oh, all right, I can catch my breath and think about other things, and or it's a refresher. And so measurements of central tendency. What is the center here? What's the sort of geographical or mathematical center of these values? That's all mean and median and mode to an extent. That's all these things are. So let's say there's a question. How many fingers does a commercial fisherman have? Okay, it's probably not 10 if you add up all the fishermen in the world. I'm sure some people have lost a hand or lost some fingers. So you do a sample. The whole population would be the population of commercial fishermen. I don't know how many that is, hundreds of thousands or something. Are we going international? Are we just in the US? Are we just in the state? I don't know. So let's just do Nebraska. Let's take a sample of 25 fishermen. So this is a sample. This isn't the population. This is a sample. The population is the entire Nebraskan, population of every commercial fisherman. We have 25 of them. That constitutes a sample. We sampled from the population, and these are their fingers, right? We have a 0. Somebody lost 2 hands and is still at it. We have somebody who lost 1 hand, and we have some people who've lost fingers, right? And then we have someone with 11 fingers. We have Christopher Guest, Tyrone Rugen, Princess Bride, if you've seen that. So right here, we have 56% of this sample has 10 fingers. So that's the mode, right? That's the mode. Never make a graph that looks like this. This is just to fill up a slide and make it look aesthetic, but these are misleading graphs because 56 and 20%, this is like, looks like everything. These little 4% are off in the distance, and so they occupy less space. Technically it's accurate, but we have this huge section down here in a 3-dimensional graph. Just never use 3-dimensional graphs because it's the proportions are distorted. But what is the difference between mean and average? Why are they separate terms? Average is the mean. Really, if you say average, it's just sort of a lazy word for the mean. Um, but the mode in this case would be 10 fingers. It'd be 10 because there's 56% of them. Mode is just the most common. Whatever the most common number is, that's the mode. So if the question is, the next person who walks in this room is a commercial fisherman from Nebraska, how many fingers do you think they have? The best answer is going to be 10, right? Because that's the most common. If your answer is 8.9 or whatever, that's nobody's going to come in with 8.9 fingers. I mean, that's not believable. And all right, a couple of questions. What's the difference between mean and average? Why are they separate? Oh, that's what I was just talking about. Well, one's more colloquial than the other. And would a sample of 25 be considered too small to really represent a population of fishermen in the state of Nebraska? Probably. Good question. That's probably too small. But we can make some statistical inferences if the magnitude is really sound. If the magnitude of the effect is enormous, what is the IQ of a commercial fisherman, or the height of a commercial fisherman, or the weight of a commercial fisherman? What is the salary of a commercial fisherman, compared to something else? And our p-value is like 0.001, and the magnitude is enormous. Now, okay, it's fine because we had this, narrow confidence interval, and we're really sure, and the magnitude was big, so it's possible. But yeah, as the question, is that too small of a sample? The larger the sample, the better, to an extent. Otherwise you're just, might just test the whole population. Then we're not really doing statistics anymore. You just have the number. But inferential statistics, or making inferences, the larger the sample, the stronger your inference, the more compelling, the more sure, the more certainty you have in it. So again, mode is just the most frequent number. The mean, right? You just add them all up and divide by the number. So if there's 25 of these things, 25 people, you add them all up, right? You get 224 divided by 25, yeah, 8.96. I'm not going to make you do this math on the test, as long as you know what a mean is. Just it's literally just the average. You just add everything up and divide by the number. But mean values might be misleading from time to time. Usually mean values are the best. From time to time, they're very misleading, and you want to use a median instead. Now, in this case, the median is 10, right? You just put them in sequential order and take the geographical center. So, this is the middle number, 0, 5, 7, 8, 8, 9, 9, 9, 9, 9, 10, 10, whatever. That's on one side. 10, 10, 10, 10, 10, 11 is on the other side. And right in the middle of those numbers, we have a 10, right? So that's the median. That's right in the center. And sometimes this is the most compelling number, the best number you can use. Now, when you get into dollars, it's often the best number is going to be the median. Remember, I have done research in healthcare, and on the finances of it, I have a publication on the cost of rib fracture care, and the median is a better value than the mean. The mode doesn't make any sense. The mode is a useless value to describe the cost of billing. But the mean, you're going to have people with $2 million bills, and that's going to those outliers are going to drag the mean way up and give this big standard deviation that doesn't really reflect what the average patient gets. What the average patient walks in there and gets, it's not really represented by the mean. It's more represented by the median in those cases. So, again, the mean, if there was somebody, if like Count Rugen, right, if he had 1,000 fingers and he was a fisherman, right, that's going to really mess up the mean, but it's not going to do anything to the median. The median remains unchanged. Now, this is the best example of what happens to a mean and a median, and how to be a reasonable person in deciding what the most appropriate statistic is. What you don't want to choose is what gives you the value you were hoping for. Don't choose like that. If you're running an analysis, often when I'm doing medical care, man, it's helpful if I use the mean. And so I have to report the median, or report the limitations of using the mean. And you have to be sort of cautious and use your head and decide which value is more appropriate, which value reflects the population better. Remember, we're making inferences about a population. If someone in the mean is messing it up, you have a huge outlier in either direction. On the low end, on the high end, a massive outlier. The mean is totally messed up. The median is unchanged. So Puget Sound, we're up in Washington, and there's a bunch of zip codes. At least last time I looked, I think there was like over 150. But Medina and Bainbridge, both really nice. Now Medina is a little bit nicer, but Bainbridge is beautiful. If you've gone through these areas, gorgeous homes, really. I mean, we should all want to live there. And if you swap in Medina, if you say like, all right, what's the net worth of the residents in these zip codes, in these two different zip codes, in Medina and Bainbridge? If you're using the mean, there's a massive difference in the net worth of these residents, right? And if you switch to the median, the Medina households decreased by $45 million. Now, this isn't like today. It's still a massive number, but this was in 2005. And we all know Bill Gates lives in that area. Guess which zip code he lives in, right? So if you either remove Bill Gates from your analysis, he's an enormous outlier, or just switch to the median, it statistically manages the outlying effect of Bill Gates. The net worth of people who live in that area is decreased by $45 million. So use your head and sort of think through the situation of which measurement of central tendency is ideal, not just because it supports the hypothesis you're hoping gets supported, right? That's cheating. Make sure you use the one that's most appropriate for the finding, most appropriate for the research question. And that just takes thoughtfulness. That doesn't take any amount of like statistics to figure it out. Maybe it does if you want to look at the difference between mean and look at the variance. If the variance is enormous compared to the mean, something like that. Okay, maybe we can consider median there. So you can do a little stats and give yourself a hint. But otherwise, it's you can sort of just eyeball it and know what the most appropriate ethical statistic is. Now, let's say you're a parent, fast forward the world, infinity years, if you're not going to be a parent, fast forward the world 20 years, and some of you have kids and you're taking them to, football practice or something. And you want to know how often are kids carried off the field in a stretcher. What are the odds that my kid is going to end up in the hospital with, potential paralysis and lifetime disability? And so, well, what are the odds? Now, let's say in a 10-game season, it was 0, 0, 0, 0, 0, 1, 1, 2, 6 at the end of the season. I don't know, maybe it's postseason, you're playing against hard teams, or your team is tired and getting injured or something. Something happens at the end of the season and people are just really being ripped off that field in the stretch. 6 stretchers in one game. Now, mode 0, right? The most common number is 0. How often are kids, carried off the field in a stretcher? It's honest to say, well, I reported the mode. That's a measurement of central tendency. 0, never. Right? But that's misleading. Now, if you say the median is also 0, the median 0, right? 0, 0, 0, 0, 0. Then we have another 0, and then 1, 1, 2, 6. And so the median is 0 as well. But the mean is 1. There's 10, 6, 7, 8, 9, 10, and a 10. So on average, it's 1. Right. And so the mean here is much more appropriate. That communicates something to the parent. How often are kids carried off the field in a stretcher? Well, about once a game. That's what the average is in this situation. You could report 0 and well, 2 out of 3 measurements of central tendency agree that it's 0, but that's misleading, right? There's a breach of ethics there. You're knowingly suppressing the reality that it's 10 kids over the course of 10 games. So make sure you're smart and ethical about which measurement of central tendency you use. Again, means, standard deviations, that's what you report. 19.7 plus or minus 1.5. That's how you'd report that one. And these are just arbitrary things I'm plugging in here. This is what your table 1 should look like. You can make it look like anything you want, but make it aesthetic, right? Make it pretty. So here are your variables over here. Each variable has its own row. And this is the total number. N just means number. So there are 45 total subjects. And let's compare in a fraternity versus not in a fraternity. So Greek versus non-figurative Greek, right? Not like literal. Let's say it was going to be like 20 and 25 or something like that. So this is the total sample. That's what your descriptives are describing, the total sample. So 20.2 plus or minus 0.7, let's say that's what your descriptive said. And the BMI was 26.5 plus or minus 2.8. So you're just putting your descriptives in here. Now, or if you can compare men to women, right? You can compare men to women, fraternity to non-fraternity, athlete to non-athlete, but you're going to have 2 other columns. So you have your total sample, everybody you enrolled, and then subsamples, put 2 subsamples in here. And then significance is the final column. Your p-value is going to be the final column. So this first row, this is the names of your kind of sample and subsample, whatever. And then your n, and then whatever variables you want to look at, pick a few. But we have these also, right? These are percentages. You don't have means and standard deviations of percentages. Nightly sleep, 7.5 plus or minus 1.4 hours. Okay, that's continuous. You get a mean standard deviation. But with, how many, um, what percentage of people have academic scholarships, that's not a standard deviation stuff. That's just what percentage of the sample, 20%, 30%, whatever. So the way you do that, let's go back to the Analyze tab, right? So we're in SPSS, we're back in SPSS, and there's that menu bar. Click on Analyze, go down to Descriptives, the side menu pops up, and go Frequencies. Frequencies is how you get frequencies. Frequencies is how you get percentages. So you click on Frequencies, and you don't put continuous data, these little scale data, right? These rulers, right? Don't put those in there. You're not going to have frequency of years of age. It's going to be a big sloppy output. Well, 19 had 4% and 20 had 8%. I mean, it's going to look ridiculous. So, but you put in stuff like sex or gender. Do you live on campus? These are all yes or no things, and it doesn't have to be yes or no. It could be multiple categories. It could be what's your political party or something, and there's 5 options or something. That's fine, but these are all frequencies, percentages. Hit OK. After dragging these in, you can either just double click on these things or click on it and then click on this thing and it'll drag it over. Click on OK, and it'll bring up your frequencies, right? So the percent and valid percent, use valid percent in the table. Now here, there's no missing data. And so percent and valid percent are the same. But if there's missing data, that's another column and the percent is reduced. But if there's missing data, like not everybody filed if they were male or female, and there's like 15 people who didn't file, who didn't report, then the valid percent would still be 26.4, but the percent would be much lower because the percent would be relative to 100 and however many people I said, 120, 130 people or something, because we would have missing data. So you just report males 26.4%, females 73.6%. Is valid percent the same thing? Is valid percent the percent from those who tested? Yes, valid percent is just the people. It's the percentage of males from the people who answered. It is the percentage of people who live on campus who answered, right? Ignoring people who didn't answer. This is just what you have data for. Here's a percentage. Report that one. Don't report the regular percentage. Now here they're the exact same number, but sometimes, like here, you can see they're different numbers. So this was an earlier class. I'll ask you guys too, and you guys don't have to answer. There could be missing data, but I'll give you a couple points of extra credit so I can run some stats on your tests. A bunch of questions about, do you believe in leprechauns and unicorns and whatever, and then what's your astrological sign? At some point I'll ask you guys this and I'll give you extra credit for it so I can use it for statistics. But this is what I did last year, and I'm using last year's stats. Missing data: 35 people didn't answer, 33 people did, and this may be a combination of 2 classes or something, but so 8 people didn't know, and so that's 11.8% if you count those 35. It's 24.2% if we ignore the missing data. Among people who answered, that's 24.2% of people who didn't know. And so that's the number you want to report. Now, it says something that some people didn't answer, right? That's some people would rather not answer. The people who would rather not answer, maybe religiously, maybe they are, I don't know, do palm reading for a living and don't want to do my version of they take it seriously and I'm not, and they're offended. I don't know. Whatever the reason. um, that's great stuff. Is valid percentage? Yeah. So I was just reading the comments. When I start mumbling to myself, when I'm talking and I'm sort of on what could conceivably be called a roll, and then I just pause and start mumbling to myself, I'm usually reading a question in that moment. So, so this is, you get the idea of valid percent versus regular percent. Same thing here. There are 34 subjects, class, students, whatever, who didn't answer, and 34 who did. And so the valid percentage is twice the percentage, right? But these are the people who have never had me before among people who answered and people who didn't answer, or people who didn't answer. Whatever, you get what I'm saying. I just phrase it horribly, but I think you get the idea on what these frequencies tell you. And so the valid percentage, that's what you put on the table. People who went to tutoring: 0, no; 1, you did. And so you would put no, people who didn't go to tutoring, 76.5%. That's what you would put in the table. And so now in the total sample, this is everybody you sampled, percentage employed. Again, I'm just making up numbers here. This isn't real stuff, but this is what you would put is percentage of people employed, 22.5%. That's it. There's no standard deviation. That's just a valid percentage that you get from your frequencies. And so that's what you put in this first column is descriptives here for age, descriptives for BMI, descriptives for GPA, descriptives for nightly sleep, frequencies for percentage employment, right? Frequencies for athletic scholarship and academic scholarship, frequencies for those two. Now, moving on to the subsamples to make those comparisons, right? If you want to do, juniors and seniors versus freshmen and sophomores, if you want to do fraternities versus non-fraternity or men versus women, whatever, you want to compare subsamples. Now we're doing compare means, right? Let's go back to SPSS to that Analyze tab, to that, you go down to compare means over here. And you scroll over. It's obnoxious because as you like reach for this box, if you don't like stay in your little column and you kind of go up, it like disappears and you have to re-click and start over. But so you go over here to your compare means, you come over, and then we're going to do an independent samples t-test because these are two independent samples. They're independent of each other. They, men and women are independent of each other. Greek and non-Greek, whatever, they're independent of each other. Athletes and non-athletes, independent of each other. Now, if you were testing students when they were freshmen and then students when they were juniors, that would be a paired samples t-test because of the same people being tested twice, paired samples. If you do before and after and you test the same people to themselves, paired samples t-test. Paired samples t-test is not two different groups being compared against each other. This is the same people. Like if it's a weight loss study and people are baseline testing and then they do the weight loss program and 6 weeks later they're tested again, use a paired samples t-test. What does ANOVA mean? We will get to ANOVA, but one-way ANOVA, when you're looking at this, what you have is 3 time points. And I promise this comes at the very end, but you have 3 time points and 3 or more. So a t-test is just 2 groups being compared. Either independent samples t-test is men versus women, whatever, golfers versus baseball players, kids versus adults, Russians versus Swedes, whatever it is. You have 2 different groups and you're testing those 2 groups against each other, but you don't have 3 groups. If you have 3 groups, you're getting into an ANOVA. Paired samples t-test. This is baseline and follow-up. But if it's baseline, mid-test, follow-up, you have 3 testing periods. Now you use an ANOVA. An ANOVA is just a fancy t-test. It's a t-test where there's multiple comparisons because you compare the first time to the second time point, the first time to the third time point, and the second time to the third time. So you do a bunch of t-tests all at once, and you have to statistically control for that because remember the jelly bean example. If you do 1,000 tests all at once, you're just going to get arbitrary significance. So especially if you consider 4 tests, if you're running 4 comparisons, then it's first to second, first to third, first to fourth, second to third, second to fourth, third to fourth. There's a lot of t-tests being run all at once. So that's what an ANOVA is. But we're going to do an independent samples t-test. So you click on independent samples. Now, the t-test, if you get a t value, that just means signal to noise. You never need to calculate it, but you do need to understand what it means. You don't need to know the formula. Again, understand what it means. A t value of 0 is just there's no finding here. There's nothing here. I mean, you have so much noise and no signal. A t value of greater than 1 means more signal than noise. There's potentially something going on. A t value of 50, and it's just like an enormous signal and very little kind of scattery noise. And what that actually means, the signal, because it's a ratio of signal to noise, the signal is the difference in means. Let's say it's fraternities and non-fraternities. I will not pick on fraternities. I will say fraternities have a GPA of 3.9, give or take 1. And non-fraternities have a GPA of 1.9. Students who are not in fraternities, give or take 1.3 or something. The signal there is 2. 1.9 to 3.9, that's 2, right? So that's the signal. It's just the difference in means. Now the noise is the scatter of the data. And this is how you calculate it, right? The standard deviation squared, right, over the first sample. So if this is like, these are the fraternities, students, and these are the non-fraternity students, whatever. We have these two different samples we're comparing, right? So if we're going to get the noise, this is how we calculate it, right? And so the standard deviation, as we know, is just a measure of the spread of the scatter of all these variables. And so this is I just made this up, right? But regret of a child's conception against age of the child in years. So with each additional half of year increment, parents are regretting more and more the conception of the child. This is just like me coming up with something insulting, but there's a bunch of variance, there's a bunch of scatter, right? And so we have this line of best fit that sort of predicts best. And if we're going to do a simple linear regression here, and we try to come up with this prediction model, but this is pretty scattered. There's a relationship here, but all these red lines, these residuals, these measurement differences from the expected, from the mean, we have to have a way of quantifying that. So let's say we did 10 exams. I'm not going to make you calculate this. You don't have to use a calculator. You don't need to remember this. You just need to understand what it is, so that when I'm talking about things like variance and standard deviation, these are coherent terms. So they sort of make sense to you, but you never need to calculate them. SPSS does all the calculations for you. So I don't need you to do math. I just need you to understand basically what it is. And I'm not even going to put the math on the test and say which one's right or what. I'm not going to do anything like that. But so you do 10 tests, we do in this class or something, and there's 67%, 77%, blah, 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 up to 95%. There's these 10 different tests. Now the mean, right, you just add them all up and divide by 10. There's 10 tests. So if you add up 95 plus 94 plus 92 plus et cetera, and divide by, because there's 10 tests, you divide it by 10, you get an 84, the 84%. That's your mean. Now, if you're going to get the variance of the mean, right, not the standard deviation, but the variance, what you do, it's a little bit more complicated. The mean is 84. So 67 minus 84 squared is 289. 70 minus 84 squared is 196. 78 minus 84 squared is 36, right? You take all of those numbers, just take every one of those numbers, add them up, divide by 10. And we get 84. So the variance and the mean are the same. They're not always the same. There's what's called over dispersion or under dispersion. Over dispersion means the variance is much larger. And so if you look back at our test, our exam, the mean was whatever it was, 78 or something, and the variance was much higher than that. So it's not always the exact same, the variance and the mean. Other than Excel, is there a quicker way to calculate it? Yeah, SPSS. SPSS just is way easier. SPSS is like beautiful software. Once you get used to it, everything has a learning curve, but you get used to it, and you just click and it just does everything for you. And it's SPSS is like Mac, where it's just this intuitive operating system. You just point and click and it does everything. Excel is a little bit, you have to like type in formulas, and it's sort of a hassle, and then you like click, and it's crazy amounts of buttons right now. I know it seems like a lot of buttons to click, but everything is pretty simple once you get the hang of it. There's the learning curve. Once you can navigate it, though, it's very fast. Trust me, it's very fast once you can navigate it. It's just like you get a new iPhone or something, some new, smartphone or whatever. And it's just for a minute, you have to figure out where all the buttons are. And then you're like super fast on it a week later. And so SPSS is similar. It's just as intuitive as Apple. That's why it's so expensive. You can get it for free because Pacific pays for it. But if you're to buy this, on the whatever non-black market, if you're to buy it on the colorless market, then I don't know, it's over $1,000, whatever it is. But there's other types of software. There's Stata, there's R, these tons of typing, and it's like MS-DOS, if you've ever used that, where you're typing in commands. It's sort of closer to Excel, but even less visual. SPSS is the most intuitive one. So the sample standard deviation and the population standard deviation. Now the standard deviation, this isn't the same thing as just the average distance to the mean. 67 minus 84, 70 minus 84. If you just take all those numbers, not square them, and divide by 10, that's a different number from the standard deviation. You don't need to calculate it. This isn't going to come up on the test. But if you know everybody in the entire population, but we're working with samples, right? We're working with samples and making inferential statistics. And so this would be the standard deviation. So it would be 84.0 plus or minus 9.7. That's how you would report the mean and standard deviation of this set of tests. And that's the math to do it. If you ever, for some reason, you're taking a stats class and you need to do it by hand, I hope this gives you the resources to do that. My class is not that class, but just to give you an idea of what these things are. So just a second ago, I said, this number is different. The standard deviation is different from the distance to the mean divided by 10, right? So there are 10 distances to the mean. So 67 is 17 points away from 84, which is the mean. 70 is 14 points away from 84, which is the mean. 6 points away, 1 point away. Like 83 is 1 point away from 84, right? 86 is 2 points away from 84. So the average distance divided by 10 is 7.6. That's not your standard deviation, which is 9.7, right? So standard deviation is a very specific calculation. Now, getting back to a t-value, 17 minutes, thanks. Mean 1 minus mean 2, that's the signal. The noise, it's a signal to noise ratio, standard deviation squared of the first sample over the number of subjects, plus standard deviation of the second sample squared over that number of subjects in that sample. You take the square root of that. So that's a signal to noise. All you need to know is that it's a calculation that includes, standard deviation, and it's just signal to noise. That's all you need to know about a t-value. So when you see a t-value of 6, that's good, it's encouraging. When you see a t-value of 0.3, there's more signal there than there is noise. That's just scatter without much of a difference in mean values of the two groups. So that's all you need to know about a t-value. What about 1? Same amount of signal and noise. Remember, 1 over 1. So the question was, what about a signal to noise, a t-value of 1? That's just the mean difference is the same as the scatter. So the signal is the same as the noise. Who knows what's there? Sort of, there's no compelling finding you can derive from that. The bigger the t-value, the better. The better that ratio of signal to noise. So let's open back up a database. This is an older one, an older grade database. I didn't want to do a bunch of this kind of live with us in it. But sex, and so gender, sex, and alphabet, where people fall, alphabetical order, their ID, their 989, whether it's odd or even, office visit, whether they had me before, stuff like that. But in this one, there's also grades and stuff. So at the top, that's the menu bar, and analyze, compare means, independent samples t-test. Now, what you'll do is you'll take a binary variable from over here, office visit, or if you had me before, I used gender, and you click on it, and then so you click on gender or whatever, and then click on this little arrow and it brings it over here, and then you click on your dependent variable, in this case exam grade. So is there a difference between males and females on exam grade? So exam grade goes in your dependent variable box, and this little grouping variable, that's your independent variable. But you have to click on this define groups button. So you click on that, and this comes up, and you have to enter in how they're coded. So males are coded as 0, females are coded as 1. You can see it here: female, 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 male, female, female, a bunch of females, male, male, female, male, male. So you have to enter those in, and then click continue, and then you just hit OK, and it gives you something like this. Now, this is an older output. SPSS changes the look of their output somewhat routinely, but you don't want to get used to the look of an output. You don't want to get used to a particular aesthetic, because in your posters, you're going to make it look different all the time. If you use different software, it's going to look different. If SPSS comes up with an update, it's going to look different. So you don't want to get used to one particular output, but it always looks something like this. Males, females. There are 17 males, 16 females. Here was the mean of this particular year. Here's the mean for females and of males, and the standard deviation. So you know what that is: the mean and the average spread of values. Now, is there a statistical difference? Look down here. This is, are the variances of these groups equal, of males and females? Do they have comparable scatter? And the answer is, yeah, they're equal. Now, if you get down to like 0.02, 0.03, 0.04, something like that, okay, now we have a problem with variances are not equal. It's called homoscedasticity. We're breaching that assumption. But as long as get this over 0.05, and people are willing to say, fine, use your t-test. And we use this top one over here. And 0.829, that means there's an 83% chance, an 82.9% chance that we would have observed a difference this extreme or more extreme than that if the null hypothesis were true. The null hypothesis here is males and females are the same. There's no difference, right? So if the null hypothesis is true, we see a difference. It says it over here, 0.94%, so almost a whole percentage point. Almost a percentage point difference. There's an 83% chance we've observed something this extreme or more extreme than that if the null hypotheses were true. So, but you see your t-value, right? The t-value is tiny. The noise is bigger than the signal, right? So the noise is bigger than the signal. If you have a significant finding, you'll see a bigger t-value. You'll see a t-value that's bigger than 1. Now the t-value, I'll probably ask about this. This is a huge researcher, William Seeley Gossett. This is where the t-test came from. Sometimes we call this thing the student's t-test. So remember the name William Seeley Gossett. This is where history occasionally rears its boring head for everybody sort of under the age of 30 and interesting head. Fascinating mouth and jawline and brow for everyone above the age of 30. But William Seeley Gossett, he was a Guinness employee. And the story goes, Guinness employees were not allowed to publish anything because their competitors could get the data, or they could get the methods, or they could get the secret tricks, right? And so William Seeley Gossett devised this statistic and published it by the name of Student. He had a pseudonym, Student. This isn't talking about students in a classroom. This is William Seeley Gossett's pseudonym was Student, and he published in Biometrica, massive journal, still exists today, but it's in 1908. And founded by Francis Galton. That was Charles Darwin's half cousin. They shared their Erasmus Darwin, the famous grandpa, and then Carl Pearson, right? Carl Pearson of the Pearson's correlation coefficient. I have no idea who this is. At some point, I should actually look him up. Teaching statistics. This is like shame on me for not knowing who that is. But Francis Galton and Carl Pearson, massive names. So they founded this in 1901. Very early on, we get Student. I actually have this article in my bedroom. And this is what we get from that inventiveness. Only Gossett important for the exam. There will be 3 names: Fisher, no Pearson, Carl Pearson, and then no William Seeley Gossett. Those 3 names you should know for the exam. So this is a modern look at what it gives you. 81. This is another old exam. 81 versus 80. Not much of a difference. And we see they meet the assumption of homoscedasticity, or quality of variances. Those 2 groups, the males and females, are variances, right? The scatter was comparable between the 2 groups. And so, but there's an 82, a p-value of 0.82. That's nothing, right? Now this one was different. This was actually last year's test. And lady folk, you killed it last year. The mean score among females was pretty much like a B, and the guys, I don't know what happened. And last year, actually earlier this year, this is the last time I taught the class. But so there actually was a significant difference. P is 0.026, and the T is negative, but between -1 and +1, that's nothing. And so negative 2.36, when there actually is a difference here, and there's a meaningful difference in means, and the noise isn't that big, we get a T value of more magnitude. And again, we meet the assumption of homoscedasticity. So you put all those in over here, right? Those are continuous variables. And so they're differences in continuous variables. That's a t-test, in this case, an independent samples t-test. And so you put them in here. Wherever you have descriptives in that first column on the total sample, you're going to run an independent samples t-test on subsamples. Now we still have these left to go, right? We have what were frequencies over here is going to be chi-squared, the difference over here. And these are the corresponding p-values to the difference between subsamples. So 21 to 22, right? P-value of 0.412. A GPA of 2.6 to 3.2. Oh, that one's significant. You always want to highlight or somehow draw attention to the significance. So to fill in the rest of them, you go descriptives, right? We're not going to compare means anymore. These aren't means. If we're going to do frequency comparisons, we're going to do what percentage of people are females and what percentage of people, if we're comparing percentages, we're comparing frequencies. Those aren't comparisons of means. You don't have means of frequencies. So you go descriptives. This is like, make sure you make a mental note of this one, or a physical note, or you refer back to this or something. The descriptive statistics, you go to crosstabs, because it's like a weird way of running this. It doesn't really make sense. It's not, this is the unintuitive one. It makes sense once you understand the stats and stuff, but it's totally unintuitive. It doesn't just say chi-squared. So you go to crosstabs. Click on crosstabs. Now the chi-squared value, not going to make you calculate it, but what we're looking for is there a difference in expected percentages? We assume there's going to be 50% females and 50% males. We assume there's going to be 25% freshmen, 25%, you make these assumptions. And does what you found breach those assumptions? That's what we're doing for chi-squared. And so you have a column and row. So let's take sex and put it in the columns and say people who know their astrological sign, yes or no. Not what the astrological sign is, but people who know it, yes or no. You could also put the astrological sign here. It just needs to be categorical. It doesn't need to be a 2x2 table. It just needs to be categorical by categorical. We had to do something with degrees of freedom by squared. Does that apply here? Oh, we're in degrees of freedom. We can talk about that later. I want to try to plow through this a little bit more, but degrees of freedom, it's not going to come up that much. We'll talk about it later. So this is sex, and do males and females, or do they differ in whether they know their astrological sign? We would expect, half of males to know it and half of females to different. Now, you can't just click OK. That's the thing. You have to click on statistics, and this box comes up. And then you click on chi-squared right there. And then you click on continue. Now we can talk about stuff like phi and Kramer's V are fine, and Kramer's V later. And we can talk about that stuff later. But chi-squared, and then click continue. Now, when you click continue, you also have to click on the cells box and then click on the column box, that box right there, and that'll tell you the actual percentages. Otherwise, it doesn't tell you percentages, it just tells you raw numbers. So it's a little bit, and then you click continue, and then you hit OK, and this comes up. This is what it looks like, where whether among females, 5 of them don't know, 19 do know. So 80% of females just about do know. 5 minutes, thanks. And among males, only about 67% of males know their astrological sign. So 3 of them don't know, and 6 of them did know. With females, 5 of them don't know, and 19 of them did know. Now, is that significant? Yeah, it's different. What percentage of females don't know their astrological sign? Oh, about 21%. What percentage of males don't know the astrological sign? About a third of them, exactly a third of them in this sample. Now, let's say, does this reflect the population? Nah, P is 0.456. There's a 45.6% chance that you would have observed differences this bigger of this magnitude or greater than that if the null hypothesis were true, meaning men and women know their astrological sign the same. Sort of unbalanced groups. There's a lot more females than there are males. And so this isn't significant. So that's what you report over here in the crosstabs. So employed, 20.4 or 24% of men were employed, 19.7% of women were employed. Is that significant? No. There's a really weak trend. It's about a 10% chance you'd have observed something that bigger. But academic scholarship, and athletic scholarship and whatever. So these, they're statistically, they weren't different. So that's your table 1. That's the first visual you always create in every manuscript that you make, in every poster, in every presentation, certainly in every lab. You make a table 1 to describe the people, you're working with, your sample. Who are we looking at? And then you tell the reader, look, I'm going to tell you about some findings we have, but first, let me tell you about my sample. Let me describe the people in my sample. And so that way you know who I'm working with. You always make a table 1. Now, if you want to start getting into relationships within the data, because that's what comes next. You've described your sample. What comes next is, all right, what the hell is in this database? Are there relationships? Do variables predict other variables? Is there something going on? So you go analyze, correlate, and then carefully track the mouse over bivariate. You click on bivariate. Now it's bivariate correlations, 2 variable bivariate, 2 variable correlations, and you're going to get a Pearson correlation coefficient. Carl Pearson correlation coefficient. Now, this is a Francis Galton idea from the 19th century, 80s or something. But Carl Pearson really developed this. And so you get this Pearson correlation coefficient, which describes the relationship. Positive one, moving in the same direction. These variables are moving in the same direction perfectly. Exactly. 0.8, ridiculously strong correlation in the positive direction. You get under about 0.3 or so, and you just sort of this kind of nothing there. It depends on whether you count that as something, but 0 is literally nothing. There is no correlation. It's just absolute random scatter. It has a correlation coefficient to 0. Over here, -1, as one variable goes up, the other variable goes down, right? As, like age goes up, I don't know, muscle composition goes down or something like that. So that would be that would be like a -0.4. A -0.1 is like a perfect inverse correlation, a really strong inverse correlation here. Get under about 0.3 or so, and you start to get into sort of that nothing. This is what it looks like. Really simple. It's going to be telling me on the 1 minute mark. I've got to be getting close. Age is correlated with pulse, with heart rate. Inversely, as you get older, your pulse goes down. Now, this is significant because I did it on 2,000 patients. 1 minute, thanks. 2,000 patients. And so earlier this semester, there was a question about that. As the sample goes up, doesn't significance just get better and better? Yeah, it becomes more obvious. A tiny effect is more detectable. It's more significant. It signifies an effect. So they just systolic blood pressure is correlated with age. As systolic blood pressure goes up, so does age. The other way, as age goes up, systolic blood pressure goes up. Has nothing to do with pulse. Systolic and pulse, nothing to do with each other. Systolic and diastolic, pretty strong positive correlation. P is less than 0.001, but the Pearson correlation coefficient is 0.6. Okay, now just really quickly, feel free to just take off. The rest of the slideshow is just, I'm going to post this, but where you can find publicly accessible data if you don't want to do your own data. Healthdata.gov, that's great. Berkeley's library, you can go there and you can find publicly accessible data sets. Eastern Michigan University's library, you can find publicly accessible data. Now, it's usually in the form of Excel. Sometimes you'll find it in SPSS, but you can open up Excel documents in SPSS. That's totally fine. It'll do that. This is a little trick to the new version where we have to put the file in a specific place. We'll talk about that later. All of these sites, no matter what you want to do, Bureau of Labor Statistics, Walmart, Airbnb, there's data everywhere. You can get, see you, Jake. See, everyone else is leaving. So just remember, this is an epidemiology class. You can collect your own data if you'd like, or you can just go get publicly accessible data, whether it's on COVID or whatever. So, that's it for today. The lab is usually held, here and here and here. Now it's held in your home, right? But Nathaniel is going to be available to help walk you through some of that stuff, to walk you through SPSS installation and SPSS use, and some guidance on running those analyses, some guidance on interpreting them. But really what you're interpreting for the first lab is just sort of, let's just go make a table 1 and run a correlation. So everything we just covered today, that's really it for lab 1. All right, any questions? I see a bunch of the mass exodus is underway. There are a bunch of departures. So, all right, I will see everybody on Wednesday. I hope you're rested and you can continue to, rest. Whatever you guys do in life, I hope that's going well. I'll see you soon.
Thank you.
Thank you.